Hello everyone. Today we're going to be looking at the inverse of a matrix, part 1. We're going to do a little recap of things we have done earlier. So the things we have learned is very simple things. What is a matrix, type of matrices, operation on matrices like addition, scalar multiplication, matrix multiplication. We have talked about powers of a matrix, transpose, and then two special matrices, symmetric and skew-symmetric matrices. In this session, I will be talking about invertible matrices. And it will be, the focus would be on, first we're going to define the invertible matrix. Then we're going to look at some of the basic properties of these matrices. And finally, determinants of a 2 by 2 matrix and how is it related to a matrix. Okay, so let's begin with the definition of the inverse of a matrix. Now, when we talk of an inverse of a matrix, very first important part is we are only going to look at an n by n matrix. Very important, guys. We're only going to look at matrices of size n. In other words, these are square matrices only. So an n by n matrix is said to be invertible if we have another n by n matrix C such that when C is multiplied to A on the left-hand side, it gives us the identity matrix of size n, as well as when C is multiplied to A on the right-hand side, it also gives us an identity matrix n. Little typos. So where In is the n by n identity matrix here. So what we say over here is that the C is an inverse of A. What simply it says is that if you're given a matrix and we say it is invertible, then we can find another matrix C such that A times C equals C times A equals identity. And you'll be saying, why do we have to write A times C or C times A? The reason is we have learned about it that the matrix product does not commute generally. So it's very important that when we are talking of an inverse, we are going to make sure that it doesn't matter where the inverse of the matrix is put, left-hand side or right-hand side. It has both to be satisfied, both of them have to give us the identity matrix. That's the key, guys. Okay, not only that matrix has to be multiplied either left and right of the matrix A, but this matrix C has a very important property. This C is unique, that there's only one C which can do that. Okay, so let's prove that. So we say C is uniquely determined by A because suppose, now this is a proof, guys, we are doing. If B is another matrix, so it's like a contradictory proof. So if I say, oh, no, I think there is another matrix B, which is the inverse of A. Okay, let's do it. So proof is we write B. Now B can be written as B times an identity matrix. Remember, any matrix multiplied to an identity will be the matrix itself. So now as we say C is an inverse of A, what does that mean? A times C equals C times A equals identity. So here when we say B equals BI, I can replace this I by A times C. So we get this one. Now we all know that the matrix product is associative. So we can have B times A and then C can be multiplied later. Okay. Now we are also saying that B is also an inverse of A. So what does that mean? A times B equals B times A equals identity. So when we group B with A, we get an identity matrix. Now identity matrix multiplied to C will give us another matrix C only. So what we notice, we started with B, we ended up getting back to C. So that basically says that C is a unique matrix. Our contradictory proof was not successful here. Now let's look at the notation. This unique inverse is denoted by A inverse C. So C, B, whatever we're saying, it is basically the inverse of A, and we represent as A, raised to the power minus 1. So it's not a power, guys, it is a notation. So that's why we say A inverse. So whenever we say A is invertible, so when we say this term, I say A is invertible, automatically you should be thinking A times A inverse equals A inverse A equals the identity matrix. Okay. Now we have another terminology for a matrix to be invertible. We say if a matrix is invertible, it's called a non-singular matrix. Otherwise, it's a singular matrix. So terminologies also play a role. And we also discussed that there's something called determinants of a matrix. So what is a determinant in this sense? Just remember one thing, the determinant of a matrix, guys, is a number, okay? Determinants of any matrix, just remember this one. Determinant of a matrix. I'm just taking a big picture. We will talk about that in the next chapter. But at this point, determinant of a matrix, always remember, is a real number. Because we're talking with matrices of real numbers here. Okay? It's always a number. It's a very important fact. It's not a matrix, but a number. So it takes a matrix and you apply the formula for finding the determinants and you will always get a number. So let's have the proper definition. It says if you have a matrix A, and what we do is we take the two diagonal entries, we multiply the two diagonal entries A with D. That's a convention we always follow. And also diagonals B and C is also a diagonal. So what we do is we take the difference of AD and BC. So we say if AD minus BC is not 0, then A is invertible. And this inverse is given by 1 over AD minus BC times. What we do? We go back to this matrix. We are going to flip the convention of the the diagonal elements. We say we flip the elements on the conventional diagonal we follow, and the other diagonal we just multiply by a minus. Now this AD minus BC, guys. So this was okay. Let me just complete it. This is the inverse of a matrix. What it says over here is this AD minus BC on its own is called the determinant of a matrix A of size 2 by 2. Please keep that in mind that we can find determinant of matrix of bigger sizes, but for this, the formula, if you have a 2 by 2, it's basically take the product of the diagonals and you take the subtraction between the two. Okay, now, if this product of these diagonals and you take the subtraction here is equal to 0, then we say A is not invertible. And we just said if a matrix is not invertible, what do we call that matrix? We call that matrix a singular matrix. Okay, we have a very, very powerful theorem. And that powerful theorem 4 says that if you have a 2 by 2 matrix, which is invertible, if and only if. So this is the short form for if and only if. So if and only if determinant of A is non-zero. So it's just like you just don't even have to do the whole process of finding an inverse. You just say, oh, let's find the determinant. If it is 0, great. It's not invertible. If it is non-zero, it is invertible. As simple as that. Now we've done a little bit of theory. We've done some new concepts. So what's the thing now? Examples. Okay, so these are the examples, guys, taken from the book as usual. The first example is this matrix invertible? What do? We take according to the determinant. So in other words, to find this matrix invertible, what do you find? We find the determinant of A. That's how we write the notation. Another notation is you can write like this, A with 2 vertical bars aside it. Okay, so what does this mean? You multiply the diagonal elements 6 times 3 minus 9 times 2. This is important, guys. we are always going to go 6. The first element before the negative sign is the conventional diagonal. We follow. So it's 18 minus 18. It's a 0. So what does that mean? Nope. A is not invertible. Okay. It says now find the inverse of this matrix A. We have to find the inverse. At this point, we have not learned how to find it, but let me just rephrase this. Is the matrix invertible? We will do that later on, how to find the inverse. So at this point, is the matrix invertible? So what's the matrix? So what do? We find the determinant of this A. What's the determinant of this A? Simple. 1 minus 1 times 1 minus 3 times 0 is what? A 0. So 1 minus 0 is a 1, not equal to 0. So what does that mean? This matrix A is invertible. Remember, we have not, as I said, I had made the mistake over here. It's a typo because we have not yet learned the ways to find the inverse. The only thing we have learned is what is an inverse of a matrix, how do we define it, and what it is relationship with the determinant of a 2 by 2 matrix. Okay, moving further, guys, we have some few properties. We are going to work on them. Okay, the first theorem, these are like, I'm going to talk about theorems and then later on some properties too. So the first, another theorem here is, which theorem 5 says, if we have an invertible n by n matrix, for every b in Rn, the equation Ax equal to b has a unique solution, and that solution is given by x equals A inverse b. Okay, so what it's basically saying is that if you are given a matrix equation, I hope you guys remember that, okay? Ax equal to b is a matrix equation. Now we are applying things we just learned about if my matrix is invertible. What does that do to this matrix equation? It helps us to find the solution of the matrix. Not only gives us the solution, but that solution is the unique solution. Very important information. Not only it gives us the solution by this formula, but it also gives us a unique solution. So the proof. Now remember, these proofs will help you practice the proofs for the questions which I will give you later, which will be in the exercises or which are in my, exams and other old exams and quizzes too. Okay, let's come back over here. Let's look at the proof. We say take any b in Rn, because remember, we says for every b. It's important. It's for every b. Okay, so for each b in Rn, a solution exists, because we said it will have a solution, and not only that, but a unique. So we say a solution exists because it's already giving us the solution. To prove that, what we do is we take A inverse b, plug it in the equation Ax equals b. So A times x is what? A times A inverse b. Now remember, from here, this is the matrix product, and it is associative. So we can change the way matrix product is done. We can multiply A with A inverse, and we know A is invertible. What does that mean? When we say A is invertible, it means A inverse equals A inverse A equals identity. So keeping that in mind, as we have grouped A with A inverse, it's an identity matrix. An identity with a vector B will give me a B. So clearly, what we have read in this theorem, yes, it is a solution. Now we are also saying it is unique. That means this x is the only one which will give us. We say, oh, suppose it is not unique. It's nice to prove by contradiction here. We say, I think there's another one which is also a solution. We say, let u be that solution. That means if AU equals B, what happens? If A equals B, A is invertible. So that means I can multiply A inverse on both the sides of the equation. So we have A inverse times AU equals A inverse B. Now A is invertible, that means A inverse A is I times U equals A inverse B. Now identity multiplied with a vector just keeps the vector itself. So we have U equal A inverse B. So we said that X was A inverse B, and then we made a contradiction. Oh, no, there's another one U, which also satisfies. So when we started with that, what happened? So we got U to be also A inverse B, which was equal to X. So we are contradicting our own statements. So in other words, what this basically says that, hey, X is the only one which will give us that solution. Okay, now we're going to use this theorem to do an example from the book. It's one of the questions from the section, guys. Okay, says solve the linear system given below using the inverse of the corresponding coefficient matrix. Okay, now things to keep in mind. We know how to find the solution of this linear system. We all know that. We can apply we can use the augment matrix, do the row reduction algorithm, and get the answer. So what we are learning now is with this new definition we have learned about inverse, we can also find the solution of the linear system without doing the whole process. So let's do it. So what we're saying is we can find a solution. Now let's write down the matrix form. The matrix form of this one is what? It's AX equals B. And we just learned in the previous slide that if A is invertible, then this matrix equation will have a solution given by X equals A inverse B. So the only thing we need to know is my A invertible? To find that, what do? We find the determinant of that matrix. If the determinant of A is non-zero, good to go. So let's go ahead and do that. Let's write the A matrix. My A matrix is what? 5, -3, 3, -2. Okay. What's the determinant of this matrix? Determinant of A is what? -10, negative of -9, which is a positive 9, which is -10 plus 9 gives me -1, which is definitely different than 0. Then by theorem number 4, we say, hey, A is invertible. Okay, so we get that. A is invertible. Okay. Now, if A is invertible, what is the theorem we just talked about? If A is invertible, then X, the solution is given by AX inverse B, and we only just then have to do a matrix product. Okay, how do we write A inverse? It's a 2 by 2 matrix, so let's do the A inverse. Now, A inverse, remember, is 1 over the determinant of A, which we have got to be -1. And then what do? We flip the conventional diagonal, that is going from top left to bottom right, flip the terms, and the other elements are just multiplied by negative. So negative of a -3 is a 3, and 3 with a -1 makes it -3. Now what was determinant of A? It was a -1, so it is -1 times -2, 3, -3, 5, and what do we get? We get 2, -3, 3, -5. So notice in this problem, we have applied so many things. We have applied theorem number 4, we have applied theorem number 5, and we have also applied how to find determinants of a 2 by 2 matrix. One simple question, 3 different things we are doing. Okay, so once we have got that, what do? We write A inverse times B. Now then after that, it's very simple matrix product. So what is it? 16 minus 15, 1. And then 24 minus 25, -1. And hey, we got the answer. Our X is 1 and -1, which will be always a solution. And this is going to be a unique solution. Okay. Let's look at another theorem, guys. That's theorem number 6. This is a very, very powerful theorem because it has a lot of different scenarios which we will be using a lot in proving our questions and using them later on in different ways. So let's start with it. What is theorem 6? Theorem 6 says if I have an invertible matrix, then A inverse is also invertible, and the inverse of the A inverse is the matrix A itself. Okay. To the proof is very simple because we say if A is invertible, what does that mean? A times A inverse equals A inverse A equals identity. And we say this A inverse is the inverse of A. Okay. Notice, we are saying A inverse was, so if we flip the roles, we say A inverse is invertible. What does that mean? A inverse is this, isn't it? Because if you multiply a matrix with another matrix and you get the identity, so it doesn't matter. We can say A is the inverse of A inverse, or A inverse is the inverse of A inverse is A. So basically, you can go back and forth of how you say it. This can be said that, oh, let me write it down. I can't even see myself what's there. Okay, so what this little product says, the way we look at it, this says the inverse of A is A inverse. Because what is the definition of an inverse? You take a matrix, you multiply it, and it doesn't matter your matrix comes first or the matrix comes second, it goes to the identity. So the inverse of A is A inverse. Now if you think A inverse, you hold on to the A inverse, and then you look at A, which is on the right, or A on the left, either way, I still get the identity. So I can use the same thing and say, hey, this is also the inverse of A inverse is A. So it's basically by the virtue of the definition of an inverse of a matrix, we say that if A is invertible, then A inverse is also invertible. And because we notate the inverse of A by A to the inverse, so A inverse, in other words, if you're going from this side, so I'm looking at this as my matrix, so what is multiplied to it is an A. Okay, the next one, very, very important. It says if you have two invertible matrices of size n, let them be A and B, then their product is also invertible, very important. If I have two matrices which are invertible, the product is invertible, and the inverse of the product is given by B inverse A inverse. In other words, if you have to prove that this is the inverse, so what we normally do, if you have to prove something is the inverse, the classic scene is you take that, if you say C is the inverse of A. So if I say C is inverse of A, what does that mean? C times A equals A times C equals identity. Do you see that here? So if I'm saying the inverse, we say if two products, so that AB is also a matrix, so you can think of AB as C. So if this AB is multiplied with its inverse, I should get, it doesn't matter the inverse is here, A on the here right hand side or on the left hand side, I should get the identity. So whenever you have to prove things like that, what you do is you take the product, here whatever you're proving, AB. You multiply B inverse A inverse on the right hand side. And then what we do is we just do normal matrix product. So AB, then B inverse A inverse. Now remember, associativity, I can actually combine B inverse first. Now, because B is invertible, what does that mean? B is invertible means B inverse equals B inverse B equals identity. So we replace B inverse by identity. And then identity multiplied with any of the matrices will have no change on the matrix. So we will have A times A inverse. Now remember, A is invertible too. So it is identity. So we have proved that when you multiply the product AB with B inverse A inverse on the right hand side, you get identity. In a similar fashion, when you multiply B inverse A inverse on the left hand side of AB, I will still get the identity. You just follow the way it was done in the previous equation. Okay, so that basically is a powerful theorem which says that if you're having two matrices which are invertible, the product will be invertible. That's the very number one information. Second, the inverse of that matrix is the inverse of the matrices but in reverse order. Now suppose I had three matrices. I would say A, B, K. And I say all three are invertible. Okay, so what would be the inverse of ABK? So ABK would be now K inverse, B inverse, A inverse. That's what it is. You write down the inverse of a product of matrices in the reverse manner. Do you remember, similar to your transposes? That's exactly what it is. Well, that takes us to the subpart, the final part, subpart of this theorem 6, which is related to transposes. Okay, here we say if A is an invertible matrix, then also the transpose of the matrix is invertible. Okay, and the inverse of the A transpose is the transpose of A inverse, which is basically meaning this. A transpose inverse is A inverse transpose. Okay, so we're saying if A is invertible, what does that mean? A inverse equals A inverse A equals R. Then we say A transpose is invertible. What does that mean? Means A transpose times A transpose inverse equals A transpose inverse times A equals identity. So that's what it is. Now what we're going to prove is that the inverse of the A transpose is basically A inverse transpose. So what we're going to do, as I just said earlier, you just have to prove that the inverse, which is of that particular matrix, you put either on the left hand side or on the right hand side of the matrix. So what we do A inverse transpose, okay, multiplied with A transpose. Now here, remember the property which we learned in the previous section where we started with matrices, that if you take the transpose, now this one, remember this one, if I'm just going to write it down, if you have A transpose B transpose, it is the same thing as having B A transpose. So we're going to use that property. So when you write it down, we'll have A inverse transpose. Now remember, A is invertible. What does that mean? Does A times A inverse is identity to the transpose is identity. So in a similar fashion, if A transpose is multiplied by A inverse transpose on the right hand side, we still get an identity matrix. The same procedure as the top. So it's basically these three properties are very, very powerful. We will use them a lot. And as I said earlier, the generalization of theorem 6b means if I have a product of n by n invertible matrices, the finite number of them, their inverse will always be invertible. The product would always be invertible. And the inverse of the product is nothing but the inverses in the reverse order. Okay. As usual, what do? We have done a lot of theory. Now examples. Okay, the first example. Again, it is from the book, guys. The section part of it. It says, suppose the B minus C, I have two matrices B and C and D, three matrices, sorry. We have three matrices B, C, and D, such that all these, matrix product and their addition, subtraction of matrices, it's all possible. That's what we are assuming. And we are saying that, so if I take B minus C times D equals 0, and if B and C are m by n matrices, and D is invertible, and this matrix product basically means that D is an n by n matrix. Remember, invertible matrices are always square matrices. So then the question is, if D is which is given us to be invertible, then this equation basically says B is the same as C. Okay, let's go ahead, do this. We are given the equation B minus C times D to be 0. Now D is invertible. What does that mean? D inverse equals D inverse D equals identity. So we're going to multiply D inverse on the right hand side on both sides of the equal sign. So what do we get? B minus C times D inverse equals 0 times D inverse. So 0, remember, is a matrix. It's not the number 0. It's a matrix, guys, because everything is in matrix form. So we get B minus C identity equals the 0 matrix, or B minus C with an identity is nothing but the B minus C, equals 0. So now it is this, so what we can do is we can add C on both the sides. So we will get B equals C. Okay, very simple proofs, guys. It's just that you need to remember the theory to do it. Okay, let's look at another example. We have two matrices of size n, say they are A and B, and we say B is invertible and the product is invertible. Okay, we have two matrices A and B where B is invertible and the product is invertible. We have to show that the matrix A is invertible. Okay, let's look at this one. We are given that AB is invertible. You say, let C be equal to this. Now, C is equal to AB. Now remember, B is invertible. So that means B inverse equals B inverse B equals identity. So we can multiply this whole equation by B inverse on the right hand side. Now C times B inverse is A times B inverse. Now remember, B is invertible. So it is A times I, which is basically A. Now let's look at this part. A equals C times B inverse. Now remember, C, guys, is invertible. Now if B is invertible, what does that mean? We just did the theorem that if B is invertible, B inverse is also invertible. Now, what is this? C times B inverse. Invertible multiplied to an invertible. That means the product. And another theorem also says that if two matrices are invertible, the product is invertible. So that means A is also invertible. Okay, guys. Now, we are going to practice some problems, and here are the problems for you guys to practice. There are questions 1 to 7, 9 to 11, 13, and 15. And I will see you in another part of the section. So, thank you.